So for the first part of our problem, we're going to be solving for the rotational inertia of this rod pivoted at this point on the end. So to start, we are going to look at this as a whole, but we're going to start with an infinitesimally small mass, right here, this little sliver, and we're going to call this sliver dm. This is an infinitesimally small mass, and this is just a little piece of the entire rod, which is mass m. And this, well, let's just say this is a distance away from the pivot point x. Now, when trying to find the rotational inertia of this rod, we have to sum up all these different masses throughout the entire rod, and to do this, we're going to be using integrals. So our integral equation for this, in this case, we know that the moment of inertia of an object is mass times radius squared. So in this case, if we're trying to find the sum of all these tiny masses in this entire uniform rod, we're going to use di is equal to dm x squared, which is similar to what we have, except we're using an infinitesimally small mass in this case. But there's a problem here. These two values do not correlate, mass and this value x, a distance from the pivot point. So now we're going to use some ratios to fix this. So from here, we're going to start with dm over dx is equal to mass over length. And in this case, dx representing the length from the pivot point to this certain mass, we're equating it to the length because this entire length of this rod is a distance L. So now we have to solve for dm to try and get these variables equal to each other. So dm is equal to mass over length times dx. We're going to take this and plug it into our equation here. So di is equal to x squared mass over length dx. So now we have this integral here, and we have to integrate it in order to get our moment of inertia. So if we integrate both sides, di, and we integrate this entire function, and we're going to add some limits of integration. So this is going to be from 0, starting at this point, which is 0, a distance away from the point of rotation. And this is the upper limit of integration, which is L, so this is going to be L. So we're going to put length up here, and we plug in all of our other information. And now we're ready to integrate this equation. So if we integrate, I is equal to, it's going to be 1/3 m over L x to the third, and then between the limits of integration from 0 to L. Now let me erase some of this so we can have some more room. There's just one more step in this process. We're going to use what we found here, and we'll bring it up here. The rotational inertia is equal to 1/3 m over L, and now we're going to plug L in, and then if we plug 0 in as well into this function, 0 in for x is just going to make this entire thing 0, so we're subtracting 0 from this, as we know when we integrate. So our inertia is equal to 1/3, and as you can see right here, one of these will cancel out, so our inertia will equal 1/3 mL squared. Alright, so now we're going to solve the second part of our problem, which is we're going to be finding the tension in the rope that is holding the rod up. So first we're going to use a free body diagram, and this will help us determine the rest of the problem. So we'll start with mass and gravity down through the center, and then up to the right we're having our tension up, and this is the point of application on this side. So it's applying its force on the very end of the rod, and this is applying it to the center. So this will be L/2. This will be length. And we're going to use this for our later part in the problem. Now, knowing that this rod is in static equilibrium, it's not moving in either direction, so therefore the sum of the torques is 0. So we'll start with sum of the torques equals 0. But we also have to establish our rotation, or which way we're going to be rotating our object if it is to rotate. So let's just say we'll set this rod as positive rotation counterclockwise in this direction. So now we can use our free body diagram to solve this problem. So we'll start with tension times length, and we don't need to use sine theta at the end of this because this is perpendicular to the rod, and sine of 90 degrees is 1, so it's just tension times length. And now this is acting in the opposite direction, so it's mass, gravity times length divided by 2. Again, this is perpendicular to the rod and it's applying perpendicular force, meaning that's just sine 90, which is 1, and this is all equal to 0. So now we're just going to solve out. Tension times length equals mass times gravity times length divided by 2. If we divide the lengths out, our tension is equal to mass times gravity divided by 2. Alright, for the third part of this problem, we are now going to be solving when actually the string is going to be cut from the rod. Now, when the string is cut from the rod, it will start to swing down. And for this particular part of the problem, we're going to find what is the speed of the center of mass when it is perpendicular to the horizontal, or in this case, when it reaches the bottom of its rotation. So, we're going to find the speed of the center of mass at this point right here. Now what we know is that the length of this rod is L. But we also know that the length to the center of mass is L/2, as you can see. So we're going to be using energy to solve this part of the problem. So we'll start with the sum of the potential energies to start, plus the sum of the initial kinetic energies, and those are equal to the sum of the final potential energies plus the sum of the final kinetic energies. So now we're going to use this equation to solve for the speed of the center of mass at this point. Now we know that the potential energy at the top is going to be mass times gravity times height. But in this case, height is going to be length divided by 2 because it's going to be falling only half the distance. So we can change our height to length divided by 2. Our initial kinetic energy is 0 because we are not moving once we start this problem. And now, when we reach the bottom, our final potential energy in this particular system is 0 because we have fallen our full distance and there is no potential energy left in the equation. So that leaves only our final kinetic energy, which is equal to 1/2 I omega squared. And this is equal to the rotational kinetic energy of an object that is rotating. So we're going to be using this to help solve our equation. So mass times gravity times length divided by 2 is equal to 1/2 I omega squared. Now, each side has 1/2. We can just get rid of those. They will cancel each other out. So mass times gravity times length is equal to rotational inertia times omega squared. Now what we know from Now what we know from kinematics and our relations with rotation is that velocity is equal to radius times omega. And now since we're solving for the velocity of the center of mass, at this point it's going to be velocity divided by L over 2, considering that's the distance of the center of mass from the pivot point, is equal to omega. So this will equal 2V over L is equal to omega. And we're going to use this in the rest of our equation. We'll also be using what we solved for in step 1, the rotational inertia, in this problem as well. So now let me erase so we can get some more room. We'll have 2V over L is equal to omega, and we'll move this up. Mass times gravity times length is equal to I omega squared. Mass times gravity times length is equal to 1/3 mL squared 2V over L squared. Now we can just use this to solve for V, so we're going to have mass times gravity times length is equal to 1/3 mass length squared 4V squared over L squared, when we square this quantity right here. These lengths will cancel out, and these masses will cancel out. So we have GL is equal to 1/3 times 4V squared. Now we multiply 3 on the other side. 3GL is equal to 4V squared, divided by 4 on each side, and then if we take the square root of all of these, 3GL over 4 is equal to the velocity of the center of mass.